Hello everyone, I'm Prabhakar Datta from the University of Connecticut. Today I'll take you on a journey through the inside of a neutron. In 1930s, the discovery of nuclear anomalous magnetic moment indicated that they are not point-like particles. It was startling, but at the same time meant that we could look inside them. In 1950s, Robert Hauser started doing exactly that. The technique is to measure the electron scattering cross-section from an unknown charge distribution and then compare that with the known scattering cross-section from a point charge to get the form factor that carries the structure of unknown charge distribution. So, elastic electron-nucleon scattering can be used to probe nucleon's internal structure. The nucleon vortex gamma is given in terms of Dirac and Pauli form factors. Their linear combinations can be used to define Sachs electric magnetic form factor G and Gm. Finally, you can define the elastic electron-nucleon scattering cross-section in terms of them, so the q-square evolution of Sachs form factors may reveal nucleon's internal structure. In 2007, Gerald Miller successfully expressed unpolarized neutrons' bright frame charge density ρ0 n in the transverse plane in terms of Sachs form factors and used the existing neutron elastic form factor data to reveal its nature. It shows if somehow this person can manage to travel at the speed of light towards an unpolarized neutron, then upon crossing its surface, first he will see an outer layer of negative charge, followed by a layer of positive charge, and then the negative core. This contradicts both Mason cloud and gluon exchange models' prediction that the neutrons have a positive core. Such a contradiction makes it of great interest to measure G and Gm at very high q-squared values, but till date, data exists only up to q-squared equals 4gv². Hence, the SBSGMN experiment has run recently in JLab's Hall A to measure neutrons' magnetic form factor GMN at 5 different q-squared values up to 13.6 GV² with very high precision. The technique is to scatter electron of deuterium target and simultaneously detect the elastically scattered electron and the corresponding nucleon to get the quasi-elastic neutron to proton scattering cross-section ratio R double prime. The next step is to get elastic scattering cross-section ratio R prime via nuclear correction and finally extract GMN. For production, SBSGMN used 15 centimeter liquid deuterium target. Scattered electrons were detected by the big bite spectrometer. Big bite dipole upbend scattered electrons, which then get cracked by 5 layers of gems with micrometer precision. And finally, they get stopped by big bite calorimeter, which measures their energy and triggers the DAQ. On the other hand, super big bite spectrometer is used to detect scattered nucleons. SBS dipole separates the hadrons by charge, and then the hadron calorimeter detects both neutrons and protons with very high position and time resolutions. Since the data taking was completed quite recently, we are at very early stage of analysis. Still, with just initial calibration, we got some very impressive results for q-squared equals 3gf². We chose LH and LD2 runs that were taken with same SBS dipole field, then projected a straight line hadron track from interaction vertex to the face of HCal using elastically scattered electron kinematics measured by big pi. Next, plotted the difference between the observed and calculated hadron positions on HCal. For LH2 data, this is a sharp peak shifted away from the origin, indicating deflection towards the top of HCal, whereas for LD2, there are two broader peaks, one at the origin and another coincides with the LH2-1. This is exactly what we expect since SBS dipole upbends protons. So for LD2 data, the peak at origin is due to neutrons and the shifted one is due to protons. This ensures detection of both quasi-elastic electron-neutron electron-proton scattering, which is necessary to get the ratio R double prime. Also, 2D correlation between horizontal and vertical hadron position differences show clear neutron and proton spots. Furthermore, it's also very encouraging to see how significantly the HCal cuts clean up the W distribution at such an early stage of analysis. Nevertheless, our immediate next steps of analysis would be to fine-tune all the calibrations. In conclusion, SBSGMN was completed successfully, and final results will greatly expand our knowledge of neutrons' internal structure. And thank you so much for listening.